Our next point in the journey is European XFEL or XFEL. And European XFEL is an international non-profit company located in the Hamburg area in Germany that is owned by 12 European countries. And the European XFEL operates, maintains and upgrades 3.4 long X-ray laser, kilometers long X-ray laser, which produces flashes of X-rays of unique quality for studies in physics, chemistry, materials research, and the life sciences. And now it's my pleasure to give the floor to Christian Bressler, Professor of Physics, leading scientist, European XFEL from Germany. Christian, do you hear us well, and are you in connection with us?
Yes, hello. Good morning, everyone, and thank you for the introduction of European XFEL. I guess I'm ready to present. If my slide is visible now, is it? Oh, fine. Excellent. Then, welcome to European XFEL in Hamburg. It's the latest newly built X-ray free electron laser facility on this planet, and I wanted to walk you a little bit through what it's all about. It started 3 years ago and with 6 specialized experimental stations, and is now ramping up to get into full power X-rays for research opportunities. To give you a little bit of broader context, European XFEL is not the only one on this planet. There are a few more free electron lasers. First, the groundbreaking linear coherent light source, or as we call it, LCLS, which was inaugurated 10 years ago, originating from the older SLAC accelerator machine. And has more or less pioneered the research opportunities we all now are building on and trying to expand further into the future. Shortly after, in Japan, next to Spring 8, Synchrotron, there's the SACLA free electron laser, which is also now in full swing and operational. And just around the time or right before European XFEL inaugurated first beam, well, the Swiss FEL went more or less online, and the Korean X-ray free electron laser went online. LCLS, which is more or less the pioneer in this field, is now entering phase 2. So they are now inaugurating, as I speak, LCLS2, which will provide even more advanced conditions, almost similar to what I will present you today as well. European XFEL is a huge installation in the greater Hamburg northwestern corner. On this aerial photo you see on the bottom right, the Daisy campus, which has the Petra Synchrotron, of which we'll hear right after this talk, and also enabling, there's a little Linux structure in the northeastern corner called FLASH. That's the femtosecond laser at Hamburg. It's enabled the technology that was then expanded up to 3 kilometers here for European XFEL. Namely this superconducting LINAC technology, which allows us to accelerate many more electron bunches than anywhere else on this planet. And then we run into a maze of tunnels, 5 of them we have, of which 3 are received by what we call scientific instruments. These are the experimental stations where you can, as a user, eventually do your experiments once you went through the application process, as pretty much as Magnus outlined earlier. It is, as of today, the strongest X-ray beam on this planet, meaning that we can allow 30,000 of these raw X-ray pulses to enter the experiment while all the others are more or less limited to 100 pulses per second. So it's almost 100 times more intense than all other free electron lasers combined. It's based on self-amplified spontaneous emission. This is a process where an electron bunch travels through a radiation generating device we call undulator. And these are just alternating magnetic fields, which in the Lorentz view of the electron frame are extremely short, and there are some tricks, and you eventually turn this sinusoidal function into a very short undulation on the order of 1 angstrom, which is the X-rays we eventually take out of that. These are accelerated and self-amplified over a fairly, well, you could say short or large distance of 100 meters is the order of magnitude, in order to then generate what we call microbunches. I won't torture you now with the details about this, and this is then the moment when we run into what we call saturation. Gives you at the end pulse energies very comparable to what you have from commercial amplified laser systems. So it's on the millijoule level, up to 10 millijoules possible, or if you prefer 10 to the 12 photons per pulse. What comes from this process, the process of generating the radiation is a stochastic process. It starts with spontaneous emission. That's on the far left corner. Somewhere here is the first photon that is spontaneously emitted in the correct direction. And that is then amplified all the way out. This leads then to some indetermination of the process itself. And that means we get first of all, we get here's a simulation of the time structure where you have many, many short spikes. These more or less originate from the microbunching. But even if I would measure the spectrum that you get out of this laser, you would also see a similarly spiky spectrum. Although it is highly monochromatic, it's not precision monochromatic. For that, we have additional schemes to further monochromatize the radiation. But at the moment, it's stable down to, it's monochromatized to 0.1%, which is already pretty monochromatic for the X-ray range. What comes as a difference to, let's say, the synchrotron you hear about in a moment, and this linear accelerator is not only the pulse structure, which is more limited to 100 picoseconds at a synchrotron, with about, let's say, 10 to the 9 photons or a microjoule per pulse, but you can squeeze everything into the femtosecond time domain, and you squeeze in a lot of photons into the 12, 10 to the 13, and maybe a little bit more is possible. This is now completely different X-radiation than I worked with almost my whole scientific career with synchrotrons, because we can do things now with X-rays that we couldn't believe possible. And here you see a 5 centimeter slab of stainless steel after 30 seconds with the X-ray beam going focused into it. You can see the exit hole where the beam comes out, and it drilled its way all the way through. And we meanwhile also managed to go through 30 centimeter thick copper slabs. So it is a powerful, dangerous beam, but it is also very bright. And if you have interest to measure something that is very subtle or very weak effects, you can do this with this X-ray beam. The experiments we do are typically done in a, let's say, radically different fashion. It's called more or less diffract before destroy. So this is now the popular way of doing protein crystallography. Namely, you don't put in a single crystal as at the synchrotron, but you have here in the fluid many micro, nano sized, nanometer, 100 nanometer sized microcrystals. And each pulse from the X-ray, so these combs are are indicating the individual X-ray pulses we put through the sample. You can then record for each pulse a diffraction pattern from a single nanocrystal. After this measurement, the crystal blows up and is gone, and you can no longer use it. That's why you need then such an arrangement to repeat the measurement to get more signal quality by flushing new, fresh nanocrystals through. And that's how you can then get high quality diffraction images coming out. This is now too technical, but I just want to highlight that wherever the sun is shining, that's where it's orange is where the light is. And so this is now the view of the 3 tunnels that we have occupied right now with certain X-ray energies. We have 1 branch for soft X radiation and 2 branches for hard X radiation. And each is feeding 2 specialized experimental setups for which the goal was to design them such that we can cover the broadest range possible of experiments that can be done. And therefore we have these funny 3-letter abbreviations, and there are always 2 instruments, and here also 2 available for scientific research. Accelerator is now in good shape and is now ramping up to the highest energies, meaning that we can get 20,000 electron volts or up to 20 kilo electron volts X-ray photon energies. And this is a first that was achieved. And right now, this from last year, values are below a millijoule. Now we can go reliably up to 2 to 4 millijoules of pulse intensity. This is now a little bit a zoom into the maze of electron tunnels. So if you look at this figure, the accelerator here on the left part is 2 kilometers long, and you don't see it. And at the end of it, we have the switch yard where the electrons are sent to one undulator, where they go straight to a second undulator, bent around the corner, and going to a third one in series. This allows us then to feed these 6 scientific instruments, as we call it, and I will present them in a moment. And you have here 2 further tunnels that are not yet equipped, but we had already started workshops with the interested user community, and we will continue this to define the needs of the community in order to make the best use of these 2 new radiation tunnels, with which we can do even further experiments. And this is still coming up. These are the 6 instruments in user operation. They were not turned on all at once, but we had them ramped from one tunnel to the next. So we started here on the left and moved slowly over to the right. These instruments all use X-rays, all are equipped with lasers to do time-resolved investigations down to the femtosecond time scale. So this is the similarity of all of the 6 instruments, and energies are ranging from the very soft X-rays, what we call is the carbon K edge, around 250 electron volts, all the way up to now starting with 20 kilo electron volts. In order to get access to these facilities, you have to have a scientific idea and discuss these, and this can be developed also with the people in charge of these instruments, of each of these instruments. So if you get in touch with them, they surely will listen to you, and then they will say either maybe you should go to Adrian and not to me, so somewhere else to discuss the idea, or they would give you some advice how to move on. And this I can only advise to do, talking to people, especially as Magnus pointed out before, talk to previous users, because they know best the language and the understanding of and have a better understanding of the instruments that exist. Here is now a short compilation of what instruments we have and what kind of scientific fields they cover. I don't think I want to torture you too much now with each single capability. I just want to mention that these experiments are involved. We have many, many pulses per second, many tens of thousands, up to 30,000 or so. And we have developed at European XFEL detectors that are capable to record a full image for every single shot. And this gives a data amount that is going through the roof. And we are dealing with this now, how to provide this vast information to the users so that data analysis and interpretation of the experiments can be done in a more smooth way. You don't have to know everything about how we record data and analyze them. Well, analyze you should know, but many details we can take over for you. So you should more or less concentrate on what you really want to measure and how you want to measure it. And depending on what kind of experiments this is, there are easier possibilities if you go to this instrument and not to that one. And this is where we can help, certainly. And as Magnus pointed out, previous users can also give very good advice how to approach these new opportunities. I'll just give you one scientific example that is more closer to my own heart. This was a last year experiment by one of the users from a university in Germany, Paderborn. And there they were aiming to observe in this bi-metallic complex. So here we have an iron-centered complex, a bridge, and a cobalt-centered complex. And the reaction was aiming to observe the departure of an electron triggered by sunlight or by a laser, in this case, going onto the ligand system, transferring over to the cobalt system, and arriving eventually onto the, and reducing the cobalt ion itself. This is important because afterwards, when this is being reduced, this chlorine atom can move out and you can attach water, split water, and this could be indeed a seed for a photocatalytic converter. And the goal of this experiment was to indeed observe that the departure time and departure dynamics, how long does it take for the electron to move over? And for this purpose, now the instrument called FXE, femtosecond X-ray experiments, was able to record both the iron signal, so the departure signal, and the arrival signal on the cobalt center. And this is pretty cool if you can have both signals at once, and you can see how something moves and nothing happens on the other side, and then it arrives, and you can monitor this. These are experiments that we can now do on the sub-picosecond down to 100 femtoseconds and partially below timescale. With this, just trigger your mind how what exactly you would like to study, and we can help on the wildest ideas and hopefully find a suitable instrument. Publications are coming out because the facility is now overcoming the bug fixing stage, and now new experiments from users are now moving out from the different scientific instruments. So this is where we would hope one of your publications would come out as well. And this brings me to my final topic that I want to present to you. How can you take part in these activities? Apart from the current initiative, do come to our users meeting. It's going to be an online event in January, end of January next year. And it is a very big event and traditionally highly visited in pre-corona times by scientists from all over Europe and the world, and Germany as well, and focusing on European XFEL and the Synchrotron DAISY. there are specialized workshops you can visit. You can think of a sabbatical at European XFEL, or even about joint PhD positions if the scientific interests are found. Before you write a proposal, just like Magnus said, keep in mind you have to justify the use of a free electron laser. That is the many photons we have. It's ultra short and it's highly coherent. Then you can contact people you know, or instrument scientists, or myself. You can discuss your idea with any instrument scientist, and you can actually also initially join a community proposal. These are collaborations of many institutes joining forces to do one single experiment in order to bring forward the field they are interested in. And you can also use one of our bio laboratories. We have several large surface of biolabs, and then you write the proposal. And the proposal review panel is consisting of external experts. Keep in mind, rejection rates are rather high, they're not too low. And also keep in mind, European XFEL is a lot more than 6 instruments. It has many, many groups and labs that you can use also equally for your research. So you're not only limited to using the X-ray beam or so. So we would hope that you would become one day happy users, as we already had last year, and hopefully again when Corona times are over. And with this, I thank you very much for your attention.
Thank you very much, Christian. And we have a couple of questions for your very well-framed and excellent presentation. One of the questions is, what is the practical advantage of using FEL rather than synchrotron light sources for industrial measurements?
Sure. This I would probably pass to our industrial expert, but I would say, put it this way: if there's anything you want to study which provides faint signals, where you need lots of flux, then a free electron laser might be the instrument of choice. Keep in mind the industrial interest that you should have one of these, and the second line here where the mouse is, many photons. This is something we have in a single pulse that no synchrotron has. It is ultra short, femtosecond short, so you can observe wave packet dynamics, which otherwise you couldn't, and it's highly coherent. So if your industrial application requires information on either of these, which require either of these 3 properties, these are the 3 pillars of FEL excellence or so, then you would not go to the synchrotron for these experiments.
Okay, thank you very much. What is used for the beam stop for this extremely destructive beam you showed?
I didn't understand. What is used for
the beam stop for this?
Yes.
Yeah.
Yes, that is an important question that also excites our safety group, our radiation safety group, a lot. But the answer is the following: you don't focus. If you have focus beam of about 10 microns up to 20 microns, then you drill through everything. There is no beam stop available. If you have several meters, usually we focus the beam on the sample and then it expands outwards. As soon as the X-ray beam is larger than, say, 500 micrometers, then you do not drill through any material anymore, and you can stop it with the usual safety precautions as you have at a synchrotron. But the safety group is very much alert that we never ever come into conditions where we could focus onto what we call Hutch walls. Then you can run into big trouble. And usually we make sure we have several up to 10 meters of air between these conditions and the wall, so that the air can take away light as well. And we saw that this is indeed possible to block the beam.
Okay, thank you. How many people come at the XFEL DESI users meeting?
Yes, this is not totally clear because many people come to both meetings, the DESI user meeting with Flash and Petra and European XFEL. But we had for all three facilities, we had last year, I think, over 1,000 people visiting, which is unique worldwide. And for European XFEL, the registrations were on a few hundred level. I think over 400 last year. So this is a superb, in pre-corona times at least, or post, superb opportunity to talk to various scientists and from all different directions, institutes, and so forth. And I hope we will be able to put up a similar program that allows such exchange this January.
Okay, and the final question that goes to you, you mentioned a couple of times that good practice is to reach up to previous users if you want also to do some connections with the laboratory. Do you offer the list of previous users? That was the question. How to contact them?
Yeah, I guess you should know them probably beforehand. The list is vast. We don't collect the list such that we pass it out, but for example, in the afternoon, you will hear from one of these users who is, I think, the last talk in the afternoon. He will present possibilities, but if you get in contact with me and say in which field you would like to investigate, I can either immediately provide such information or pass on to people who would know better which one to contact best. It's not a secret, but it's we just have very many users actually.
Okay, thank you, Christian, very much, and also for showing the clear way, clear path, how to move forward if there is such an interest and initiative. Thank you very much.